All right, we're recording. So next up, we're going to go ahead and start with 5.4. Man, that glare is something. Okay, so 5.4 is all about the properties of logs. I'm going to try to turn off that light and see if that plays a little better where it's kind of a funky glare. There, that does seem to be better. Okay, so again, 5.4 is all about the properties of logs. Now, the good news is this is really simple in premise. The problem comes with the examples that they're going to ask you to do. So the properties, there's three. So you've got what's called the product property, which states, so if we have a log of some products, if we're multiplying, okay, so we've got the log of one thing times something else, we can expand that to the log of the first thing plus the log of the second. So this is what's referred to as the condensed form. This is what's referred to as the expanded form. And I'll show you in the examples, we'll actually convert back and forth between the two. So sometimes they'll give you the condensed form. Oh, come on. Okay. Sometimes they'll give you the condensed form and then you'll have to rewrite it expanded. Sometimes they'll give you the expanded form and then you'll have to turn around and rewrite it as condensed. And we'll do a number of examples so you can see what that looks like, but that's the initial property. So when you have a product where you're multiplying, that can be rewritten as the sum of two individual logs. So again, condensed is one singular logarithm, expanded is multiple logarithms. Similar to the product property, we have the quotient property. Okay, and the quotient property, just like the product property, says in the condensed form, if you're dividing two quantities, that can be rewritten as the difference or the subtraction of multiple logs. So again, the product can be rewritten as a sum, division can be written as a difference. And again, in condensed, there's only one log. In expanded, everything gets its own log. The last one is what's called the power property. And it says that if you have some power, we can bring that to the front as a multiplier. Okay, and in essence, this is really all there is to the notes of how that goes. So the rest of this is going to be how we can apply these properties to either condense or expand logs, and then how we can use it to solve some things. So the next is going to be just examples of all of these properties. So hopefully you have these written down, because I'm going to kind of refer back to them whenever I work through some examples. But these are the three properties. So again, going from condensed, one log, to expanded, multiple logs, times becomes plus, division becomes subtraction, powers come to the front as a multiplier. And again, they're going to have you go in both directions. For example, they may tell us to expand the following, and they'll give us something like the log sub 3 of x y to the second z to the third. So they're throwing kind of a couple of these properties in all on the same problem. And ultimately this sub number in this case doesn't necessarily matter. Whatever your sub number is just going to carry over to each of the logs when you expand. So the way I would do this problem, so if I'm expanding from one singular log, each of these terms is going to get a log. So I'm going to end up with 3 logs when it's all said and done. There's going to be one for the x, there's going to be one for the y, and there's going to be one for the z. So again, condensed is one logarithm, expanded, everything gets its own log. And I left some space in between there because we've got some other stuff we got to do here. For example, each of these products, these multiplications, become additions. So again, just like up here where product became addition, multiplying this x and this y squared means we're going to be adding. Okay, multiplying this y squared and this z cubed means we're going to be adding. So the multiplication becomes addition whenever we expand. And then also any exponents, remember exponents become multipliers out in front. So this y to the second power, that second power goes to the front. So we'll get a 2 there. And likewise, this cubed power with the z will get pulled to the front. So instead of a z to the third, we pull that 3 to the front and we'll get a 3 there. So this is what we refer to as the expanded form of our initial problem. So again, the property is not too difficult. Just the problem is like it all kind of gets thrown together and it's really easy to make a silly mistake. For example, forgetting to pull your exponents to the front or forgetting to change your multiplication to addition or not having a log for each of those individual terms. There's a bunch of different places to kind of throw away points here and there. So make sure you're being meticulous. Okay, take your time, follow all of your properties. Your properties also work for natural logs as well. So if they said something to the effect of the natural log of 5x over y to the second. So this is again a separate problem where they're going to ask us to expand. The natural log follows all of the same properties of your log of any base. Okay. And remember that log with the base, I almost forgot that 3 needs to be present on all of those. So whatever your sub number is, make sure you keep that with each of the logs. My pen's cutting out on me. All right, that's better. Okay, so whatever the sub number is, make sure you keep that with all the logs. If you have a natural log, there's no sub number. It's E, it's implied, we don't mess with it. But again, it's going to go. So again, 3 terms here. So we're going to have 3 logs. We're going to have one for the 5. We're going to have one for the x. And we're going to have one for the y. So again, in this case, each term gets its own log. Again, multiplication becomes addition. Division becomes subtraction. If you have any powers, those come to the front. So if we were expanding, we would get the natural log of 5 plus natural log of x minus 2 natural log of y. And again, this is your expanded form. Next, one of the curveballs they may throw at you is radicals. Now, what makes this a curveball is looking back at your properties. Okay, none of these deal with radicals per se. I don't see any square roots, cube roots, fourth roots anywhere up in here. So this is where you got to remember from a couple of chapters ago. Okay, there's another way to write that fourth root. So remember back in the days, all right. Okay, going back in time, if we wanted to rewrite the fourth root of x to the third when we were talking radicals, remember we can rewrite this as x to the 3/4 power. So any exponent goes to the top part of the fraction, and that root number goes to the bottom part of the fraction. So when you have any kind of radicals, any kind of roots, make sure you rewrite them as fraction exponents. So before we can even get started, we need to rewrite these using fraction exponents. So this is going to be log of x to the 1/4 power over y to the 3/4 power. Realize I wrote that pretty small. So again, that becomes log of x to the 1/4 power over y to the 3/4 power. And remember, when there's no exponent, or if you don't see it, that exponent is a 1. That's why it was 1/4. Okay. So even though there was no exponent with the x, it's assumed to be a 1. So that becomes x to the 1/4, and then that becomes y to the 3/4. So now whenever we expand, we're going to have two logs, one for the x and one for the y. Those powers are going to come to the front, so we're going to get a 1/4 log of x. We're going to get a 3/4 log of y. And again, that division becomes subtraction. So that's going to be my expanded form. And that's a lot of what, in fact, that's about half of what your homework is going to be. Half of the problems are doing this expansion, where they're going to give you some kind of condensed log, and then you're going to be expected to expand that log. So again, pay attention, make sure we're not making any silly mistakes, because it'll give you kind of one go at it, and it'll remind you, it's like, hey, remember, you need to do this, this, and this. And if you try again, it's like, nope, wrong answer, try again. You only get a few tries. So make sure you're getting all your points on your homework. Next, they're going to basically do the exact opposite. Instead of giving you an expanded log, they're going to turn around, or sorry, instead of giving you a condensed log, they're going to turn around and give you an expanded log. So they may say something like, condense the following. And they'll give you something fun like 2 log x plus 3 log y minus 1/2 log z. Whoa, super bright. Okay, so again, they're going to give you something like 2 log x plus 3 log y minus 1/2 log z. So this is the expanded form, and they're going to tell you to condense this. So again, when you condense, it's going to be one singular log of something. And now in this case, there was no sub number that you see. It's automatically a 10. If there is a sub number, you'll just keep it with it. So if this would have been, say, log sub 2, then this would also be a log sub 2. So if there is a sub number, you just keep it. Anyway, we work those same properties just in reverse. So numbers in front become powers. Addition becomes multiplication. So this is going to be x to the second times y to the third. And then minus becomes division. So minus or divided by z to the 1/2 power. Ooh, come on, zoom, focus. My camera's struggling. Okay, so again, that'll be the, I'm shaking. That was going to be the log of x squared y cubed over z to the 1/2 power. Now, the good news is, too, you can leave that as z to the 1/2 power. My math lab will accept it. I will accept it. Z to the 1/2 is perfectly fine. Okay. If you remember from the examples we did before, okay, z to the 1/2 power, you could also write it as the square root of z, which would be fine too, but it's not necessary. So at this point, you have your choice of either or. One is not more right than the other. My math lab and I will accept both. So you've got the option. If you'd rather write it with radicals, fine. If you would rather write it as a fraction exponent, also fine. If they gave us something like natural log of x minus 3, and then some brackets. Natural log of x minus 7 plus natural log of x plus 7. This is about as ugly as it gets. This is kind of a hairy problem. This is one of those things where they've kind of thrown everything at you. They've got some algebra concepts in here. We got some just kind of math concept. Anyway, this is a hairy problem. We've got a lot going on. So I'm not having to slide side to side. I'm just going to do it kind of below. Okay. Remember, when we condense, we're eventually going to get this down to one singular log of something. So that's what we're looking to do. So when we condense, there's nothing going on in front of the log. Okay, you're not going to have a log on top and a log on bottom. There's just going to be one singular log of something. Okay. And order of operations says we got to work kind of from the inside out. So this bracket behaves like parentheses, that's grouping. Okay, so we've got to do this. So remember, plus means 2 times. I'm going to kind of draw this over here so I can walk you through it. Remember, when you're multiplying quantities, so this is the algebra that they're throwing in here. So if we're multiplying these two pieces, remember, we got to FOIL those together. We got to distribute. So x times x is x squared. X times -7 is -7x. 7 times x is +7x. And +7 times -7 is a -49. If we combine those like terms, the -7x and the +7x cancel, and we're left with x squared minus 49. Okay, now remember, okay, that piece is kind of what's going on here. This number, then it becomes a power. So this 3 being multiplied, remember your properties, multiplication becomes a power. So that's going to be x squared minus 49 to the third. And again, this minus means we're going to be doing division. So this is going to go down here like that. So again, the x minus 7 times x plus 7 became the x squared minus 49. The minus made it division, so that's what we're dividing by, so that's why it's going down here on the bottom. And the 3 became the power, so that's where all that stuff came from. And then this x, okay, is our only positive thing, so that's what's going up on top here. So again, if I kind of pull this up where you can see that a little better, we get the natural log of x over the quantity x squared minus 49 to the third power. This is as ugly as it will get. They will not give you anything uglier than that. I did not put one that ugly on the test. To me, that kind of goes above and beyond the scope of what we're trying to accomplish. Okay. I think a problem dealing with properties is very clearly expressed of the problem like this one. This is just something math teachers do to just throw something ridiculous at you just to see if you can work your way through the process. Not me, those mean, seductive math teachers. And last but not least in this section, they could give you a problem like so. This one's kind of separate or in addition to, but it starts bringing in the concept of E and natural logs. So remember, E and natural log are the inverse operations of each other. So first off, remember, E is a number like pi. E is about 2.718-ish. Okay. And natural log is log base E. So anyway, these two things written like so cancel each other out. So if they told us to simplify this, okay, this E and this natural log basically cancel each other out. So E is a number, natural log is log base E. So E to the power of natural log is just whatever is here. So that would be that 2x minus 3. So again, E to the natural log of some thing is always just going to be that thing. That E and that natural log cancel each other out. In very much the same way, if I said the natural log of E to the third power, oh my goodness, I don't know why my focus keeps kicking out. Anyway, if I said the natural log of E to the third power, that would just be 3. Again, the natural log and the E cancel each other out. They are inverse operations of each other. So in premise 5.4, pretty straightforward. 3 properties. For expanding, multiplication becomes addition, division becomes subtraction, powers go to the front. If we're condensing, that just works in backwards. So the powers or numbers in front become powers, subtraction becomes division, plus becomes times. So again, this is the whole of the notes. The rest is just various examples of how it all plays out. And you can see that the problem is in the problems where they throw the kitchen sink at you, including, elements from previous chapters of dealing with radicals, or polynomial. So they're going to throw a couple of curveballs at you. So just be ready for that. Now, 5.5 to me is basically the meat and potatoes of this chapter. This is what this chapter is all about. 5.5 is solving exponential equations. Okay, they're going to give you some equations to solve. That's the premise of algebra. That's what this whole class is really about. 9 times out of 10, we're solving for x in some way, shape, or form. Like we've learned various operations and things we can do, but the premise is the same. So we're trying to isolate x by always doing the opposite operation. To get rid of addition, we use subtraction. To get rid of multiplication, we use division. Okay, so now they're going to give us problems that look like so. Okay, 6 to the x power is going to be equal to some number, in this case 7,776. Okay, now we could kind of guess and check this, and occasionally you'll get pretty little whole number answers where we can do just that. So we can just kind of guess and check here. So maybe 6 to the 6th power, I don't know. So again, pulling out my handy dandy calculator, if I type in 6 to the 6th power, okay, there we are. All right, that's 46,656. That's obviously way too big. But if we try 6 to the 5th power, come on, there we are. 6 to the 5th power is that 77.6. 7,776. So in this case, x has to be 5. Now, that's all well and good if you get a pretty little whole number answer. Most of the problems do not. So there is a much better algebraic method for solving. Okay, guess and check is a method. It is by far not the best. So we're going to solve this same problem using a different method. So that's 6 to the x equals 7,776. And again, we don't know what power this is going to be. So we're going to use our properties. If we take the log of both sides, come on, there we are, focus. Okay, then we can use our properties to bring our x to the front. So that's going to give us x times the log of 6 equals the log of 7,776. And then algebra says if we want to get our x by itself, to get rid of the multiplying, we can simply divide. So the exact answer is the log of 7,776 divided by the log of 6. Most of the time we're going to be rounding, so I'm going to go ahead and plug this into my calculator. So hopefully you can see, you got a big shadow from where I'm at, so you can't really see the exact buttons. But when you hit the log button on your calculator, and then that 7,776, make sure you close your parentheses so we actually do take the log of that number. And then we're going to divide that by the log of 6. Again, make sure you close your parentheses. And then hit equals. And our calculator says 5. So we're going to use logs and the properties to allow us to solve our exponential equations. And again, this works really good whenever you don't get pretty little whole number answers. For example, okay, whole new problem here. If I said 3 to the x power equals 5. Okay, this is clearly one where guess and check would stink as a method for solving, because 3 to the first power is 3, but 3 squared is 9. We're going to fall somewhere in between. And it's not a pretty decimal. It's going to be an ugly decimal. It's going to go on for a while. Okay. My math lab wants you to round to 4 decimal places. So we're going to go ahead and practice doing that. So we'll round everything to our 4 decimal places, but we'll follow the same steps. So we're going to log both sides, which lets me bring my exponents to the front. So I'll get x log 3 equals log 5. And again, to get x by itself, we're just going to divide. So x is going to equal the log of 5 divided by the log of 3. And I'm going to go ahead and write my parentheses in here because your calculator is going to go ahead and put those in probably. And you need to make sure you're closing those parentheses. The biggest mistake people will make is actually a user error while typing it into your calculator. If you hit log 5, but you don't close your parentheses, okay, then your calculator is essentially figuring the log of 5 divided by the log of 3 and then taking the log of that, okay? So that's not what we want. We want to take the log of 5 as a number divided by the log of 3 as a number. And then we're going to get some crazy wackadoo decimal. So log 5, close parentheses, divided by log 3, close parentheses. We get about 1.464973521. Okay, and as a reminder, we're going to 4 decimal places. So all we do is look at that next number. This number being bigger than a 5 is going to round that up. So we're going to get 1.4650. Now you can go back and check your answer by plugging that in for x. But remember, if you plug in the rounded number, you're not going to get an exact answer. You're going to get something really close to 5, but it's not going to be exactly the same. It's going to be similar but different. Okay. So anyway, if you go to check, if you have this number stored in your calculator, it'll actually work exactly like it's supposed to, because this number is stored in your calculator as exact. But if you try plugging in the approximate number, you're going to get something close to 5, but not exact. Now, again, that's the simple version of what we're doing. Of course, it's a math class. They've got to take things and make it more complicated. They're throwing some more steps in here. So they'll say something like, solve for x. They'll give us something like (3 to the 4x minus 3 power equals 7. Now it's going to start out solving the same. Again, log both sides, pull your exponent to the front. So we'll get quantity 4x minus 3, because that's my whole exponent, this whole thing. Okay, times the log of 3. And that's going to equal the log of 7. And again, we're trying to get x by itself, so the opposite of multiplying is to divide. So we will do so. Now, we don't just have x over here by itself. So again, algebra still holds true. We want to know what x is. Okay, we don't necessarily care what 4x minus 3 is. We want to solve for x. So we're not done canceling or basically eliminating stuff. So if we want to get rid of this -3, okay, we got to add 3. And to get rid of the 4, we're going to divide by 4. Now, again, this is the exact answer, but we're going to get the decimal approximation. Make sure when you plug it in, you're plugging in this entire quantity kind of the way it looks, or do it in stages, which is kind of how I would recommend doing this. So for example, I would type in the log of 7, close parentheses, divided by log of 3, close parentheses. So again, oh, you can't quite see that. I'm typing in, so log of 7 divided by log of 3, making sure to close my parentheses, and I'm going to hit my equals, and I'm going to get some crazy wackadoo decimal. Leave that decimal stored in your calculator. I mean, you can write it down if you want, but don't round it yet. We don't want to round until we're finally done. Okay, so I'm going to leave this number stored in my calculator. And now I want to add 3. So I'm just going to hit +3 equals. Okay, and that added 3 to my decimal. And same thing, now I need to divide by 4. So divide by 4, hit equals. And that's when I get this whole honking decimal, this approximately 1.192810937. Okay, and again, we're rounding to 4 decimal places. This number is smaller than 5, so we can just truncate it. Those go away. So the final rounded answer is going to be about 1.1928. Make sure you do not round until the very last step. If you round early, okay, then you're making an approximation based off of another approximation. It allows for error. Okay, the last thing you want to do is do all of the math right, but then have the computer count your problem wrong because you're off by like 2 decimal places. Okay, so don't round until the very end. Leave that number stored in your calculator while you do the rest of the math to it. All right, new problem. All right, so let's say they gave us e to the 5x power equals 4. Now we can still log both sides, pull the exponents to the front, okay, divide, but we can actually shorten this just a little bit. Okay, if you remember from like 2 seconds ago in our notes, remember to get rid of e, we were able to use natural log. Natural log and e are inverses of each other, okay? So if you need to get rid of e to solve for x, we can simply use the natural log. And using the property from last time, so the natural log of e to the 5x power is just that 5x. And to get x by itself, the opposite of multiplying is to divide. So x is going to equal the natural log of 4 divided by 5. So remember, that's a different button on your calculator. Okay, usually right by your log button, there's an ln button. So we're going to use that natural log button. So the natural log of 4, close your parentheses, divided by 5. is about 0.27725888722. And again, rounding to 4 decimal places, that 5 is going to cause that to round up. So we're going to do 0.2773. Okay, so remember, if they give you an e to some power, to get rid of it, we're going to use the natural log instead of using just the regular logs. Now, there are two other types of problems that they're going to give you. Okay, they can also give you a logarithmic equation instead of an exponential equation. And we can solve these as well. This actually goes back to 5.3, where we first learned about logs, and we're just going to solve this one by rewriting it. So remember, given a logarithmic expression, we can rewrite this as an exponential function. So remember, the sub number is your base. Whatever the log equals is going to be your exponent. Then whatever you're taking the log of is the answer to the exponential function. So if we simply just rewrite the log as an exponent, this whole thing means 5 to the 4th power is going to equal your x. So to solve for x, all we got to do is take 5 to the 4th power. So 5 times 5 times 5 times 5, or if we type in 5 to the 4th power, that would be 625. Now they can give you something similar. So completely separate problem. So we've got the log of 2x minus 1 equals 1. We're going to solve this one in the same way. Just what you have to remember is when there's no apparent base, it's a 10. When you just have a log, that's log base 10. So when we go to rewrite this one, this is saying 10 is the base. This 1 is your power. And then your answer is what you're taking the log of. So that 2x minus 1. So 10 to the 1st power is 2x minus 1. And again, now we just have a straight up algebra 1 level equation. So 10 to the 1st power is 10. If we want to solve for x, to get rid of our minus 1, we're going to add. 10 to the 1st power is 10. 10 plus 1 is 11. Divide, divide. X is 11 halves, or 5.5. I don't care which answer you give, they're the same. We've been doing answers in decimal form, so if you want to do 5.5, that's fine. If you want to leave it as 11 halves, fine. Pay attention to what my math lab wants. I don't think it matters, but if it says round to the nearest whatever decimal place, I would give the decimal answer, not the fraction answer. Now, the curveball they may throw at you here is taking something from the previous section and throwing it in. So it gave us the log of x minus the log of x minus 3 equals 1. Now, because we have multiple logarithms, we can't do our rewrite. We can't write this as x to the first. Anyway, we can't do a rewrite with our exponents because we have multiple logs. So you got to go back to the previous chapter. We need to condense this. We need to take these multiple logs and we're going to rewrite them as one singular log. Okay, so we're stealing from those properties from section 5.4. Remember, when you're subtracting, we can condense that to a division problem. So the log of x minus the log of x minus 3, as long as you have the same base, this becomes the log of x over x minus 3. And now that we have our one singular logarithm, we can do the rewrite. So we take our base, which again, if there's no apparent base, it's a 10. So we've got 10 to the first power is going to equal x over x minus 3. Okay. Now with multiple x's, we got to get this x minus 3 off of the bottom, so we're going to multiply. So we'll get x equals, we distribute 10x minus 30. Okay, we're going to get our x's on the same side. 1x minus 10x is negative 9x. Divide, divide. X is 39ths or 10/3 or 3.3 repeating. Again, the big take-home thing is when you have multiple logs, you can't do your rewrite until you condense that down to one singular logarithm. So you got to use your properties to condense this first. Then we do our rewrite. Then we use our algebra to solve the equation for x. Apply to get rid of your denominator, distribute, combine your like terms, multiply by the reciprocal. Simplify your fraction. Now, there's one other concept, another type of problem they're going to give you that looks similar, but you actually solve it differently. And the reason is you're going to have a log on both sides. So for example, if you have a log on both sides, so before, again, looking at our previous examples, we just had one log equaled something. So we did our rewrite, okay, with our exponents. So base to power equals answer. In this case, when you have a log on both sides, we're going to solve this one differently. So remember, these are quantities. And when you're solving an equation, this says that these two quantities are equal. Well, it only makes sense that the log sub 4 of some number is going to equal the log sub 4 of some number. So if I'm taking the log sub 4 of this, and I'm taking the log sub 4 of this, Well, the only way these two things can be the same is if these two numbers are the same. The log sub 4 of 5 is not going to equal the log sub 4 of 3. That doesn't make sense. The only way these can be the same is if these two quantities are equivalent. So if you get the same log on both sides, they ultimately don't matter. For these two things to be equal, you just have to take what the log is and set those equal. So same concept, just with a hairier problem. So let's say we got the log of x plus the log of 3 equals the log of x plus 1. Okay, just like before, if you have multiple logarithms on the same side, okay, we've got to condense these. We can't deal with multiple logarithms really at the same time. So we're going to condense this using our properties. Okay, remember addition, we can simply rewrite as a product. So the log of x plus the log of 3 is simply the log of 3 times x. Again, addition becomes multiplication. Now, also, once you have your logs, okay, again, the log of some number equals the log of some number. These can only be equal if these two numbers are equal. So that's how we set this up. So we're going to set it up where 3x equals x plus 1. And then we'll turn around and solve that. So we'll get our x's on the same side. So 3x minus 1x is 2x. Divide, divide. X is 1/2, 4.5. Okay, two big take homes. Again, if you've got logs on both sides, remember for these two quantities to be equal, okay, these two quantities have to be equal. The only way the log of something will equal the log of something is if these two somethings are the same. Take home number 2, if you have multiple logs on the same side, we got to use our properties to condense. Okay, yet again, so the hairiest problem you're going to get within this chapter is something gross like so. So we've got the log sub 4 of x plus the log sub 4 of x plus 1 equals the log sub 4 of 2 plus the log sub 4 of x plus 3. All right, there we go. Hairy problem. Lots of stuff going on here. And in fact, the way we're going to solve this makes a call back to another previous chapter. So anyway, I'll walk you through this one. Again, multiple logs on a side, we got to condense. So addition is going to become multiplication. I'm going to go ahead and distribute. So if we're multiplying x times x plus 1, I'm going to go ahead and distribute. That's going to be x squared plus x. So that's just changing this to multiplication. Then I went ahead and did the multiplication. I distributed. Same here, we have 2 logs on this side. So we've got the log sub 4 of 2 and the log sub 4 of x plus 3. Again, addition becomes multiplication. So I'm going to go ahead and distribute, and I'm going to get the log sub 4 of 2x plus 6. Once you have the log of a quantity equals the same log of the quantity, the logs don't matter, and we just set our quantities equal. Now, unfortunately, fortunately or unfortunately, here's the callback. Remember, now we have an x squared. We're dealing with a quadratic. So if you go back to a previous chapter where we solved quadratics, we're going to invoke that 0 product property. So we need to get everything on the same side. So I'm going to subtract 2x and I'm going to subtract 6 from both sides. And then remember, solving a quadratic, you can use the quadratic formula. I showed you how to solve it using the calculator, or you can factor. I'm going to factor because this one factors easily. But remember, you can solve using any of the methods we've used for quadratic equations so far. So if you want to use the quadratic formula, fine. If you remember how to make your calculator work, you can use that. But anyway, I'm going to factor x squared is x times x. We're looking for 2 numbers that multiply to get -6, that are going to add to get -1, which would be -3 and +2. Set those equal to 0. And x could equal 3, or x could equal -2. Now, here's something we have not had to deal with a lot, and that is something called an extraneous solution. And long story short, basically this is a solution that says we did all of the math right, and this number should work. However, if we try plugging this -2 into our original equation where it should work, it will not. Okay, due to some properties that we've dealt with before, you cannot take the log of a negative number. If you try taking the log sub 4 of -2, or really the log of -2, or the natural log of -2, it won't work because you're asking, okay, 4 to what power is -2? And there's no power that'll change a positive number to a negative number. So this, even though it should work, according to math, it is an invalid solution. It is undefined and therefore not a valid solution. So our only solution is the 3. So just pay attention whenever you're solving, make sure none of your logs are being taken of a negative number. That is by far the hairiest problem you'll see in this section. They do throw one of those at you in my math lab, but you can walk through it. And the big trick is just remembering how to solve a quadratic. All right, home stretch. Last section of the night is 5-6. And we're going to be doing some going back to my math lab here, because this is all about applications. Applications. Okay, which is it? Oh my goodness, that green doesn't pick up really well at all, does it? It's basically just a fancy way of saying word problems. They're going to give you some context. Goodness gracious. They're going to give you some context for these log problems. They're going to show you some times where you would have an exponential function that you can solve. So first and foremost, anytime you're dealing with an exponential growth type of problem, they will almost always follow along this pattern. Okay, that's a p sub 0 times e to the kt power. So you should be able to take the information you're given within the problem and plug it into this formula. So this p sub 0 refers to your initial amount of whatever the heck you're dealing with. So whatever you started with, that's what's going to go here. So that's going to be your initial amount. Remember, E is a number, okay? Remember on your calculator, it is shift and then ln or second ln. If I can zoom in here, come on, camera. Right above the ln, there we go, is your E to some power, okay? So you need that E button. We're going to use the E button on our calculator. Okay, so wherever your calculator is, you have an ln button, okay? The operation above it is almost always E to some power, so you'll hit shift ln or whatever to get the E. Okay, this K is your constant. It's a multiplier. Sometimes you'll have to solve for that. I'll show you a couple of problems where you will. If they give you a percentage, it's almost always what would go here. If they give you a percentage, you're going to need to be able to convert that to a decimal. So for example, if they gave you 5%, you need to remember that that is 0.05. Okay, so whatever decimal, if they give it to you as a percent, we need to convert that to a decimal. And then T is going to stand for time. So they're going to give you some various problems that are going to plug into that formula. Somebody had a question? All right, thought I heard something. Not sure if it'll be easier to look at some of the problems in the book or to go through the My Math Lab. So we'll just go off of My Math Lab. So I'll pull it up. So I'm going to share my screen here in just a second. Share my screen, should be able to see. There's that guy. All right, hopefully can you guys see that? It should say 5.6 applications and models, growth and decay compound. Not sure if I can zoom this in. Anyway, hopefully you can see this on your screen. There's a word problem. It says in 2012, the population of a city was 5.88 million. The exponential growth rate was 2.79% per year. So they're going to ask us to do some things. So we're going to find the exponential growth function. We're going to estimate a population. Then we're going to determine when a certain population would occur and find the time it takes to double. So they're actually giving us a multi-part problem. So I'm going to try and write some of this stuff down, and then we're going to work our way through this. So again, point A. So we had 5.88 million people in 2012. And the growth rate is 2.79%. Okay. Oh, also pay attention to on here in the word problem. So where we're finding the exponential growth function, it's basically saying where t is the number of years since 2012. So it's setting 2012 as the starting year. So if you put in 0, that's the year 2012. So when it's talking about 2018, that would be 6 years from 2012. So I'm going to come off of this screen. So whenever I do, we're going to need to remember that. So basically everything starts at 2012. And then we'll go from there. Okay. So we stop sharing, go back to where we were. Okay. So remember, the initial growth function looks something like this. Initial amount times E to some constant times T. Okay. So my initial amount is that initial population. So that's going to be 5.88 million times E. Okay, and now they gave us a percent, so we're going to need to change this to a decimal. So that's going to be 0.0279. That percentage is your K value. And then time is the thing we don't know. So that's our variable. So part A was asking for the growth function. So this is the growth function. Okay. Then part B was asking, okay, so what's the population for 2018? They're just asking us to plug in our T value. So we take our growth function, so that 5.88 E 0.0279 T, but we're going to plug in. So again, remember, T at 0 is 2012. So T is the years since 2012. So 2018, okay, means 6 years past 2012. So you got to make sure and plug in a 6 here, not 2012. So make sure you do that correctly. So that's the number of years beyond 2012. So then if we just plug this into our calculator, so 5.88 times E to the 0.0279 power times 6, it gives me some 6.95 yada yada million. I don't remember what my math lab said. I'm going to guess it said rounded 2 decimal places. If it said round to the nearest 1, we would say 7.0. I'm going to round to 2 and say this is going to take, or our population would be about 6.95 million people. I didn't remember exactly what it said to round to, but this would be if it said to round to 2 decimal places. If it said to round to 1, that 5 actually rounds the 9 up, so that would round to 7.0 million. So depending on the rounding, that would be your answers. Now, part C said, when will the population reach 10 million people? So now we've got our growth function. And we're trying to figure out when we would get to our population of 10 million people. So in 6 years, we had almost 7 million people. Okay, so we're going to see how many years it's going to take to get to 10. So really, we just have an exponential function to solve. So this is, again, going back to the previous chapter. So the opposite of multiplying is to divide. Let's just do that. So 10 divided by 5.88 is 250/47 or some wackadoo decimal. Okay, I'll just leave it as 10 divided by 5.88. It's a crazy decimal. I've got it stored in my calculator. We'll walk through that. And then remember to solve an E function to get rid of E. We're going to natural log. And last but not least, to solve for time, we're just going to divide. So divide by that 0.0279. So time is going to equal this exact answer, but we're going to figure out what that is. So if I take the natural log of 10 divided by 5.88, close my parentheses, and then divide that by 0.0279, that will happen in approximately 19.03. So we'll say about 19 years. Remember, that's after 2012. So that would be roughly the year 2031. Or, yeah. Okay, so again, that's part C. So when will the population reach 10 million? That would be the year 2031. Part D said, when will the population double? This is basically the same problem here. We're just not waiting for 10. We just want to double that initial population, but it's basically going to be this exact same problem, just with a different number here. So if we double our population, we take that 5.88 times 2, that would be 11.76. So again, we're just solving for when the population is going to double. Otherwise, it's going to be pretty much that same problem. So again, we're going to divide. To get rid of E, we natural log. To get rid of the multiplying, we divide. So time is going to equal the natural log of 2 divided by 0.0279-ish, or about 24.8 years after 2012. So if we round to the nearest year, that would be at approximately the year 2037. All right, that's basically what they're going to ask you there, but we're going to do a couple more word problems just because they love to throw just little bitty tricky things at you. So again, I'm going to share my screen here in just a second once I pull up the right problem. So if I go back here, study plan, I want not that one. There we go. That's the one I want. All right. So now if I share my screen, there we go. Okay, so again, hopefully you're seeing this. So the 5.6 applications and models, growth and decay. So it's talking about carbon-14. So we've got a radioactive element, carbon-14. Has a half-life 5,750 years. Okay, that means every 5,750 years, that's going to cut in half. The amount you're going to have is going to cut in half. Okay, we found a bone from a mastodon that has lost 64.8% of its carbon-14. So the question is, how old are the bones? Okay, so I'm gonna, again, stop sharing, go back to my screen so we can kind of walk through this. So again, the problem says we got carbon-14, has a half-life of that 5,750 years. We got a bone that lost 64.8%. So now the question is, how old are the bones they found? So we've got a couple of things we've got to do here. All right, so we've got our initial amount, which we don't know, times E to the multiplier we don't know, times time, which we don't know. Okay. And again, that's going to equal 64 point, or actually it's lost 64.8%. So this is the curveball they're throwing at you. So if something is lost 64.8%, how much does it have left? Okay, 35.2%. Of that initial amount. So we've got a couple of things to deal with. All right, so that initial amount, we don't know, but we know we've got 35.2% of it left. Now, the multiplier we don't know, but we've got some stuff to go off of. So the half-life is 5,750 years. So anytime you're figuring half-life, we take the natural log of 2 divided by whatever the half-life is. So this, come on, focus. You can do it. There we are. So this natural log of 2 divided by 5,750 is what's going to become my K value. Okay. So the initial amount we don't know. Doesn't really matter. I'll show you why here in just a second. But again, when dealing with a half-life, it's the natural log of 2 divided by whatever the half-life is. So that's going to be our multiplier. Okay. The solving part is going to be about the same. So if we would divide by this initial amount, it doesn't matter what it is, those two are going to cancel out. So then as a decimal, what we have is 0.352 equals E, the natural log of 2 divided by 5750 times T. Whoops, there we go. Okay, now you can see what I did. So again, I changed that 35.2% to a decimal. When I divide out that initial amount, it cancels. We're left with E, and we still have that half-life formula as our constant. And again, just like before, to get rid of E, we'll use the natural log. So the natural log of 0.352 is going to equal this value times T. So we'll just divide by that value. So handy dandy calculator says natural log of 0.352 divided by, and again, you're going to need to put this thing into parentheses just the way it looks. When you divide, you're going to divide by this whole quantity to make sure you divide by the whole thing. So we're going to divide that by natural log of 2 divided by 5750. And again, we don't want to round until the very end because we don't want to drop any significant decimal places. And we get roughly 8,661.5. So we'll call that 8,662 years. Okay, and that's basically the type of thing they're going to have you do. They're going to walk you through the problem, or no, they're not going to walk you through the problem, but they're going to give you a couple of different word problems. The good news is there's only, I think, 4 problems in this section, and they all play pretty close to the same. On your test, it'll be a problem just like one of the ones that we covered here in the notes. So that's what I got. There will be a test next time, so there will be no instruction, but make sure you are wherever you need to be to take the test. So again, Adrian, I'll have your test in there where you can take it tomorrow. Everybody else, if you're signing or taking it at one of the Proctor sites, make sure you get your appointment set up to do that. Otherwise, it'll be just like we've done the last 2 tests. So if you've got any questions, you can ask them. I'm going to be around here for the next half an hour. I got to upload the video and stuff like that. If not, that's all I got for you guys tonight. And we'll see you next week for the test.
I've actually got a question about last week's assignment.
Okay.
From the homework.
Okay.
Okay, so on homework 5.2.
Okay.
I kind of was trying to figure out what the base meant, not basement, but like the base actually meant.
Right. I got it.
For the graphs. Can you kind of give me like kind of a.
Ultimately, the base just establishes the curve. So with 5.2, we were talking about graphing functions. Wow, that doesn't focus very well. But the difference between, say, y equals 3 to the x power compared to y equals 2 to the x power, the 3 to the x is just going to be a steeper curve. Okay, so 2 to the x is going to be very flat. It's going to cut through at 1, and it's going to go up like so. Okay, that's a typical exponential function. Okay, if the base number increases, you're just going to get a faster rising curve. You're still going to get the same asymptote, and you're still going to go through at 1. It's just going to be a steeper curve. So this is the 3, and this is the 2. And we're just doing a sketch of the graph. So ultimately, to us, it doesn't matter. Okay. If you needed to physically know where this specific point is compared to this point, it would definitely matter. But for all intents and purposes, we were just working on the shift. So like this moving it up left and right, or this moving it up and down. Just the base number affected how steep the curve is.
Okay. Yeah, that's what I was curious about. I was messing with it earlier. That was the only thing I got hung up on was a couple of questions left. And I was like, I'm just going to ask.
Yeah, oh, definitely. I like it. So, and it's easier to ask in person a question like that too. That'd be hard to word via email. But yeah, it's just how the curve is.
Okay, cool. That's what I was curious. It totally makes sense.
Awesome. No problem.
All right. See you next week.
See you next week.